Hello class, we are continuing with the PK model following a single IV bolus administration. As of now, we have covered two PK parameters, the elimination rate constant K, the volume of distribution VD, and now we are covering the third parameter, which is the half-life or T-half, one of the very important PK parameters. The definition, as we know, is the time required for drug amount or drug concentration to decrease by 50%. So if we have a concentration time graph, of course, on a semi-log scale, we will get a straight line. And on this straight line, we can determine half-life by measuring the time required for any plasma concentration to decrease by 50% of its value. For example, if we start at the 400 milligram per liter, which happens at time zero, half of 400 is 200. It looks like we needed 5 hours to achieve the 200 milligram per liter. So this should be the half-life. And if you check the time from 200 to 100, again, it will be 5 hours. And this is a strong evidence of the first order elimination kinetics. The half-life is concentration independent. Whatever we go from 400 to 200, 200 to 100, 100 to 50, you will end up by the same half-life value, which is different from the zero order kinetics. If you remember from our first lecture, with zero order kinetics, half-life is dependent on the drug amount or drug concentration. Like starting from 100 milligram per liter, you will need longer time to go from 100 to 50 than going from 50 to 25 and so on, because an evidence of the zero order elimination kinetics is some PK parameter, including half-life and K. These parameters are concentration and dose independent. That's why like the half-life value, you will get a different value. It depends on how much the dose was, how much concentration you are starting with. So this is the first thing we should know, the difference between first order and zero order elimination kinetics. In half-life is dose independent for first order kinetics, but dose dependent in zero order kinetics. Also, half-life has a good utility similar to the elimination rate constant. Half-life can help us to describe the elimination process. Is it normal? Is it faster than normal or slower than normal? So from the value of half-life, we will be able to describe the rate of the elimination process. Okay, I don't usually expect you to derive the PK equation, but at least you know how did we end up by this very commonly used equation for half-life. Half-life and K are described by this equation. Half-life is 0.693 over K, or K 0.693 over half-life. And we drove this equation from the equation that describes the elimination process. At half-life, when we are at T-half, the CPT at that time is half of the initial plasma concentration. If we follow this process, you will end up by this equation. At least I do expect you to be familiar with this equation. How do we determine half-life? You can determine half-life by two ways, either the graphical way or mathematical way. The graphical way, as I described before, if you have concentration time data and you plot them on a semi-log scale, you will end up by a straight line. Then you can stop at any plasma concentration and determine the time required for this plasma concentration to decrease by half of its value. Again, if you are in first order kinetics, you will end up by the same half-life. Also, we can use this equation to determine the half-life mathematically, assuming you know the two plasma concentrations and the time difference between them, you will be able to determine K as we described before. Once we get K, we can use this equation to determine half-life. Okay. Similar to K, elimination half-life will help us to describe the elimination process. So let's take this example. Assuming we have a patient with an intact kidney function, and we are giving this patient a single IV dose of a drug that is eliminated almost completely by the kidney. So the kidney function for this drug is very crucial. So assuming intact kidney function, this drug has a half-life of 1 hour, and if we do the math, your K will 0.693 per hour. Let's see what will happen if this patient lost 2/3 of his kidney function. Now the remaining kidney function is only 33%. With this decline in kidney function, you will have a proportional decline in K and a proportional increase in half-life. Means because of the slower elimination process, the drug will have a longer half-life and the drug will stay longer in the circulation. Makes sense. With even more reduction in kidney function, only 15%, you would see an increase in half-life, prolongation of half-life from 1 hour to 6 hours, and a proportional decrease in K to 0.115 per hour. Again, this is a significant decrease in the elimination rate. And because of that, the drug will stay even longer and will accumulate unless we adjust the dosing regimen. So let's take an example. If our drug has a minimum effective concentration of 10 milligram per liter, see the dosing regimen for a patient with a normal kidney function, we will give this dose every around 12 hours. Because by 12 hours, plasma concentration will reach MEC, so we have to give another dose to keep the plasma concentration above the MEC. For the second condition, when the patient has only 33% of his kidney function, because of the slower elimination process and the prolonged half-life, plasma concentration reached the MEC at around 25 hours. So in this case, instead of giving the drug every 12 hours, we have to extend the dosing interval to 24 hours. Similarly, for the last case, we achieved the MEC around 48 hours. So we will give the drug every 48 hours. So you can see how we use this information to adjust the dosing regimen for our patient from every 12 hours to every 24 to every 48 hours. If you don't do that, if you don't adjust the dosing regimen and you keep giving the drug every 12 hours in these two situations, you are accumulating the drug in your patient and you expose the patient to high risk of toxicity. So longer half-life means slower rate of elimination and the drug molecules stay longer in the circulation. According to this, as a clinical pharmacist, you must adjust the dosing regimen. Someone may decrease the dose, or the most common approach we do is we give the same dose, but every longer dosing interval to avoid drug accumulation and toxicity. Let's apply the concept now on these two cases. I gave you 3 drugs, tetracycline, ampicillin, gentamicin, and fluoxetine. They have different half-lives. My first question here is, which drug is eliminated at the fastest rate after IV administration? So we can use, as always, the half-life or elimination rate constant to describe the rate of the elimination process. I gave you half-life. If we are looking for the drug with the fastest rate of elimination, this means we are looking for the drug with the shortest half-life, right? So it looks like ampicillin. has the shortest half-life. This means ampicillin is eliminated at the fastest rate among these 4 drugs. Which drug requires more frequent administration? Of course, the drug with the short half-life will require more frequent administration. So again, ampicillin will be the drug that will be administered more frequent. The third question is, which drug will produce the highest initial plasma concentration after administration of 10 milligram per kilogram dose? So this is a very tricky question. If you remember from the VD lecture, the initial plasma concentration, or CPO, we can determine from this equation, dose, the IV dose, over VD. So I am asking about the CPO. Which drug will give me the highest CPO if we give a dose of 10? So I gave you the dose of 10 milligram per kilogram. But you need the volume of distribution to be able to calculate CPO. But if I didn't give you VD, you will not be able to calculate CPO. So in this case, you don't have enough information. And I intended to give you this case because as a pharmacist, you don't jump into conclusion and recommend a dose unless you are sure you have all the information. You may need the body weight of the patient, the age, the other disease condition, the kidney function, liver function, serum creatinine, whatever. So you have to make sure you have all the necessary information to be able to recommend a safe and effective dosing regimen. In this case, you can easily say, I don't have enough information. That's okay. Case 2 will be the same situation, but I am asking the opposite questions. I'm asking about the drug with the slowest rate of elimination, the drug that requires the least frequent administration, and the drug will produce the highest CPO. So I will give you a chance to work on this case until we see each other during the Q&A session. This is a very nice application question to the concept of half-life. A drug has a half-life of 6 hours. Approximately how much time is required for 97% of the IV dose to be administered? I will give you the clinical application of this question. For many drugs, we try to avoid giving them together, like drug A and drug B. We don't want them to be in the system at the same time. So if I took this drug that has a half-life of 6 hours, and the physician wanted me to add a drug B, that I don't want drug B to be in the system while drug A is still in the system, I have to make sure the amount of drug A remaining in the system is very insignificant, which is like maybe after we lose about, or we eliminate about 97% of the drug, the remaining portion, or like 3% or less, is insignificant. So we use the concept of half-life in this situation. So if we understand the definition of half-life, the time required for the drug amount or drug concentration to decrease by 50%, we'll be able to actually calculate the time to eliminate 97% of the drug. We start with 100% of the dose in the system. After one half-life, we end up by 50%. A second half-life, we have 25, and so on. So after all of this, we end up 1, 2, 3, 4, 5 half-lives. After 5 half-lives, we have about 3% remaining. And this is right. We usually wait about 5 half-lives to make sure we have eliminated 97% of the administered dose, and now it is safe to add a new drug to the system. So this is a good example of connecting science to practice. Some drugs have very short half-life, but other drugs have very long half-lives by days. Like you have a drug like this drug has a half-life of 2 weeks. So in a situation like this one, you have to wait for about 10 weeks before adding another drug that may have a severe interaction with this drug. So this is a very important concept we use in clinical practice. Okay, so this is my summary slide for half-life. The time required for plasma concentration to decrease by 50%. In first-order kinetics, half-life is dose and the concentration independent. Very important, which is different from the zero-order kinetics. The half-life depends on the efficiency of the eliminating organ. For example, if the drug is eliminated by the kidney by urinary excretion, then if the kidney function is intact, half-life is normal. If there is any impairment in kidney function, half-life will become longer. We depend on the half-life on designing the dosing regimen, especially the dosing interval. The length of the half-life determines the dosing interval for the drug. That's why some drugs you have to give them every 4 hours, others you can give them every 8, every 12, every 24. Some drugs we give them every week or monthly, every month. And of course, the unit for half-life is time, like we can say the half-life is 1 hour or 1 day and so on. Hopefully, these are my learning objectives. As always, please spend time going over them, and I'm looking forward to see you in the Q&A session. Good luck. Bye-bye.